Now we'll see view serializability. To understand view serializability, we should understand view equivalence first. I am going to prove that two schedules are view equivalent. That means their results are same on database. So according to view definition, this is a different perception. We'll see how these view conditions are explained or otherwise defined. So first of all, we have two conditions for read and one condition for write. So we'll see that two read conditions first. Stop the video and you read it. For each data item A, if transaction Ti reads that initial value of A, then transaction Ti must in schedule S dash also read the initial value of A. This statement says that if any transaction reads initial value of the variable A, same thing should happen in another schedule also. Then we say that the condition number 1 is satisfied. Now second condition is for each data item A, again same thing, if transaction Ti executes read A in schedule S and if that value was produced by a write of A operation executed by transaction Tj. This statement says that there are two transactions Tj comma Ti in your schedule S, let's say. Now Ti is reading a database item A and which is produced by Tj. That means before this read it is updated by Tj and immediately after that Ti is reading before others update. Then we say that here the transaction Ti is reading the data which is updated by Tj. So for simplicity, I simply say like this: Ti is reading from Tj. That is what my meaning. Otherwise, so Ti is reading the data which is updated by Tj. If this is the case, same thing should happen in another so-called schedule S dash, which we are going to prove that equivalent to S. If really these two are equivalent with respect to view definition, condition number 2 should be satisfied. What is that? If any transaction reads from another transaction Tj in one schedule, in another schedule also same thing should hold good. That's it. So now finally these two things can be merged and we can say like this: if in any schedule, if transaction Ti, let's say this one, reads database item from database, any database item A from database, same thing should happen in another schedule also. If this transaction reads from another transaction, same thing should hold good for another schedule also. That's it. This is read condition. So we can merge these two and we can say that this is one read condition. There is one write condition. We will see that. What is that write condition is, for every data item, if some transaction Ti writes it last. So we say that Ti is last writer in schedule S. We are talking about schedule S. In schedule S dash also we have transaction Ti, correct? So that Ti should be last writer. So whoever is the last writer of some database item A, in that other schedule also the same transaction should be the last writer. Then we say that these two transactions are these two schedules are satisfying write condition. That's it. Now we'll check these three conditions. Otherwise I can say two conditions: one read condition, one write condition for two schedules, and we'll try to understand this concept. For that I take these two schedules and I explain the read condition first. Let me merge these two and see here. Take every read. So because of this condition, we have to execute this condition for every database item and for every read. Take this read now. Now ask Mr. T1, you are reading from database, correct? No one is updated it, right? So here same thing should happen, correct? T1 here also reading from database. But it is not only for this read, for every read. So we have to go for this read also. Now this read is not reading from database, it is reading from T1. So you should understand the understanding. That means what is my meaning? That means I am not saying that no one can read from directly from other transactions, right? Everyone will read from database, but this read is reading the value from database, of course, but which is updated by whom? T1. So that in simple words I say that T2 is reading from T1. That's it. Now here if you focus on such read here, it is not reading from T1, correct? It is here reading from T1, but it is reading from database, correct? Fresh data, not T1's data. So finally read condition got violated, right? But don't stop. We want to check every condition. What is the reason? Just to understand this concept. But generally, now we can stop and we can say that these two are not view equivalent. Okay. Now we will see other read operations. No, there is no other read operation. So every read has been checked, correct? Now we have to see for every database item only last writes. So what is the last write here? Who wrote last? T2. Then here also you identify who wrote last T3. So condition is again violated. So two conditions got violated, that's why these two are not view equivalent. Understand? Now we'll take some examples and we check the view equivalence first. After that we will see what is view serializability. Okay. Now we'll see this example and we'll check whether these two schedules are view equivalent or not. This is, let's say, S, this is S dash. So blindly apply the two conditions. One is read condition, second one write condition for every database item. So that means what? Every read we should check. Take every read. So this read on database item A is reading from database. So there is one corresponding read here in other schedule that also should read from database. Yes. So read condition is satisfied. But only one read condition, right? Only one database item is satisfying that one. We have to try for every read. So here you see read C. It is reading from, anybody is updating C. Is there any write of C? No. That means though it is placed here almost in bottom, but still it is reading from database, right? Now focus here. Obviously this read of C also reading from database. Yes, this read condition also satisfied. Every read in that way we have to check. Don't miss any read. Now this one I missed. Let me check that. So read of B is reading from, see, any writers of B? No. So that's why definitely read of B is reading from database. Before read of B, if there is write of B either here or here, then we say that read of B is reading from the transaction. But that is not the case here. So read of B is satisfied. Now once reads are over, we have to see only last writes. So in last writes, here if you see how many database items we have, A, B, C. For every database item we have to see the last writer. For A, who is the last writer? Only one writer is there. Then definitely he will be the last writer, because when there are multiple writers, then we should check whether who is last writer, correct? Obviously T2 will be, last writer. Here also T2 will be last writer, right? Not a problem. Now go for B. Any writers? One is here. Anything else? No. When there is only one writer, automatically he will be last writer in both of the schedules. Nothing to check. Now C. For C there are two writers, right? Now who is the last writer here? T3. Then same thing should hold good here also. Yes, write of C, write of C. Last writer is T3 here also. Then all the conditions got satisfied. We say that these two are view equivalent schedules. It doesn't mean that this is view serializable schedule. I did not teach you what is view serializability, right? I just taught you what is view equivalence. These two schedules are view equivalent with respect to view definition. That means their results are same. Understand? That means if because of this schedule, if some database state is something S, let's say S1, then because of this schedule also same database state you get S1. That means every variable will have same value. That is what the concept of equivalence here. So these two are finally view equivalent. Now we will see what is view serializability. Okay. Now we'll see view serializability. In view serializability, we are going to use view equivalence. So a schedule S now is called view serializable. So view serializable intuitively means good schedule. If it is view equivalent to some serial schedule, that means according to view definition, a schedule is called good if it is view equivalent to some serial schedule, right? Whenever it is view equivalent to some serial schedule, then automatically I can say that serial schedule's result and this so-called view serializable schedule's result is same on database. That's why it is good. That is the way we can prove that a schedule is view serializable, then it is good. Now you have some schedule. Now how to prove that it is equivalent to some serial schedule? Then only it will become view serializable, right? But unfortunately there is no easy mechanism. We have to try all possibilities. So that's why the only technique according to this definition, if I follow it exactly, then we have to take this schedule and we have to compare with all that 4 factorial serial schedules. We know that there are 4 factorial serial schedules. It takes a lot of time. In general case, if you have n transactions, then the number of serial schedules possible is n factorial. In the worst case, the conditions we have to check for n factorial combinations or n factorial possibilities. Take this schedule and take one of the serial schedule out of n factorial, let's say s1, then next s2, s3, so on. We have to take up to n factorial, and we have to check view equivalence between s comma s1. If it doesn't work out, then we have to compare s with s2, s with s3. If your fate is bad, so everything will go wrong, then only we can say that it is view, not view serializable. If at least one comparison leads to, that means at least one comparison gives you yes answer, that means when s is equivalent to some serial schedule, then we can say that it is view serializable, right? In the worst case, what can happen is all these comparisons gives you false answer, that means s is not view equivalent to s1, not view equivalent to s2. When will we realize it? After comparing against every serial schedule. It takes lot of time because there are n factorial serial schedules. When n value is 100 factorial is very huge. That's why. Is there any known algorithm which can solve this problem easily? No. This problem is actually NP-hard problem. So I will teach you what is NP-hard problem when I discuss TOC, theory of computation. At this moment, just remember that NP-hard problem is very hard, and to solve that problem, every case we have to examine. Usually the time complexity of such NP-hard problems will be exponential. That is enough at this moment. Now finally, given a transaction list, otherwise schedule, checking whether it is view serializable or not, for that there is no easy procedure. Then in the GATE exam, how to solve it? But we don't have easy procedure, but we have some shortcuts. So we can use some of the read conditions, and we can get some necessary things, but not sufficient. What I want to say is, so I am not using brute force technique. I am not using this method, whatever I told you, right? It takes a lot of time. Rather than that, what we do in exam, we impose some necessary conditions. For GATE exam especially, so they give questions such a way that necessary conditions will help you in pruning some of the possibilities. Your schedule might be equivalent to serial schedule 1, serial schedule 2, anything, right? This is the potential possibility. Now, what I am going to do is, using some techniques and heuristics and using the conditions, otherwise, I am going to automatically filter out some of the schedules which are not at all possible. In that way, I will try to reduce the size of the possibilities. We will see that. However, in the worst case, these kind of things might not work for general problems when you have hundreds of transactions. But in GATE exam, they give you only 3 transactions, otherwise 4 transactions. Then how many serial, example, let's say here there are 4 transactions, right? Then how many serial schedules are possible? 4 factorial. So don't evaluate every possibility, but using some conditions, read and write conditions, whatever we have studied, I am going to cancel out some of the possibilities out of 24. In that way, I will try to reduce the number of possibilities. Then we will try to check that view equivalence for only that remaining combinations. Let's do it so that you can understand it. Otherwise, you can't understand it clearly. Let's take this example and try to cancel out some of the serial transaction schedules which are not at all view equivalent to this one. Okay, so let's do it. For that, we have to see the read conditions. Let me put 4 vertices like conflict serializability graph, T1, T2, T3, T4. Let me say it is view precedence graph. Now this view precedence graph is going to help you. That's it. It will not solve complete problem. It will just help you. How we will see. First, go to read conditions. This T2 is reading database item A from where? T1. That means if and all if this schedule is equivalent to some serial schedule, on that serial schedule also same thing should happen. Correct? For that, this T1 in that serial schedule also should appear before T2. Then only it will happen. Otherwise, if you interchange these two, if T2 appears first, then T1 in the serial schedule, then this read will read from database, otherwise from something else. That's why, because of these two, then I realized that T1 should appear first. That means we are just talking about serial schedule. Which serial schedule is going to be equivalent to this one? We are guessing. But whatever the serial schedule, and that order of that transactions T1 comma T2 should be T1 followed by T2. Sir, why not T2 followed by T1? If it is T2 followed by T1, T2's read will be before T1's write, then T2 is not reading from T1. That's why the necessary condition 1 I got, that is T1 followed by T2. This is compulsory. Similarly, now what I want to say is, sir, what is the usage of this one? Why are you doing this one? Initially we had 24 possibilities, correct? What are they? Let's say transaction 1 means 1, T2 means 2 in that way, T3, T4. Let me use numbers 1, 2, 3, 4. 1, 2, 3, 4 is one serial transaction schedule, right? Second one, 2, 1, 3, 4, another serial schedule. In that way, there are 24 serial schedules. We don't know this schedule is equivalent to which one. But because of this condition just you got now, so the any serial schedule, if it is possible, then in that order should be 1 followed by 2. Then we can remove this 2 followed by 1. In 24 schedules, almost half 1 by 2 are having this order. That's common sense, right? So because there is no relation between 1 and 2 in general in mathematics. So 1 and 2 are quite independent elements. Then the number of permutations are possibly equal to 24. Out of them, 1-2 combinations are 12, 2-1 combinations will be 12, half and half, correct? So that's why I can say that just because of this condition, I have cancelled out 12 possibilities. They are not at all equivalent to this schedule. Similarly, we'll try more conditions and we'll try to prune some more not possible solutions. Now reads are done, right? Now we'll go for last write. Who is the last writer? The last writer is C, T4, correct? Since T4 is writing last, if and all if this is this is equivalent to some serial schedule, on that also T4 should be last writer. But any competitor who are all writing that A, T1 is writing, T3 is writing, T4 is writing. Then definitely T4 should be done after T1 and after T3. Let's picture it. T4 should be after T1. Let's mark like this, and after T3. Remember. So this is the final conditions. So I got few conditions, not all. So using these conditions now, I can somehow sort it out. See. So you tell me how many possible orders we can form. One is now, if I follow these conditions, one is T1. So definitely, see, T1 should be before T2, T4, correct? T3 also should be before T4, correct? So for that one possibility I write randomly. Is it possible T1, T2, T3, T4? Let's check it out. See, T1, after that T2, yes. T1, T4 order, correct. T3, T4 order, correct. But T2, T4, there is no order, that's why, nothing to satisfy, nothing to follow. Correct. So finally this schedule, whatever it is satisfying these conditions, but it doesn't mean that this is definitely view equivalent. The reason, so we just followed some essential condition, right? Some necessary conditions, but not sufficient. But still, what I want to say is take this serial schedule now and check for view equivalence. Now, what is view equivalence? We know that. Check now again every read condition, every write condition, right? So we'll see that. Now are we really following the conditions one more time? Yeah. Read. It is reading from T1. Here if I do this one, so T2 is reading from definitely, because T2 before T2 we had only T1. That is the only write we have before T2. Then definitely T2 is again in this one also reading from T1. Perfect. Now last writes. T4 should be last write. Yes, T4 is last write. So finally, I formed some conditions and I got some serial schedule, right? So definitely this is the schedule which satisfies view equivalence. That means this schedule is view equivalent to this schedule. So this is serializable. Now we'll see some more so that you get experience. That's it. See this example. So again for this also, rather than going for 6 possible combinations, I don't check with every combination. That is actually the general method. Rather than that, we try to eliminate some of the serial schedules which are not at all possible. For that, we do like this: T1, T2, T3. This graph is going to help. What are the potential possible serial schedules which are going to be equivalent to this one, right? So let's do that. For that, we use conditions. Read of A, reading from database. Any competitors or any writers? Yes, T2 is writing, T3 is writing that A. Try to understand. Since T2 and T3 are writing the database item, then if really T1 has to read from database, then T2, T3 should not occur before T1, correct? So that I can put in a graph form, otherwise conditional form like this. Finally, T1 should occur before T2 and before T3. T1 should be before T2, T1 should be before T3. That's it. So using read condition, I got some necessary requirements, correct? So now definitely T3, T1, T2 serial schedule cannot be the possible candidate. Why? We know that order should be T1 followed by T3, then only that schedule can be equivalent to this schedule, right? So what is our final goal? Try to understand. Proving that this schedule is equivalent to some serial schedule, and I'm cancelling out some of the unnecessary schedules which cannot be view equivalent to this one. That is what the goal. Now last write. What is the last write? T1 is writing last, especially database item A. But who are all other writers? T2 comma T3. Then really T1 has to, if T1 has to write last, then T2 T3 should be before T1. Let me put it in this graph. So T2 should be definitely, so T1 should be last. Then I can say like this. Order between T2 comma T1 should be like this. Order between T3 T1 also like this, then only T1 will be last writer, correct? Let me put this structure here, T2 to T1. So now we are forming cycle. Whenever we form cycle, then that cannot be, I will tell you, that cannot be view serializable schedule. Now T3 to T1, let's put it. So what I want to tell you is, whatever the conditions you imposed on this graph, because of that, the serial schedule you are forming is having cycle. That in serial schedule you can't have cycle. That means you can't have interleaving. The meaning of cycle is interleaving. You see, T1 should be first, then T2. One more condition says that T2 should be first after the T1. That is only possible if the schedule is, transactions are interleaving. So interleaving is not possible in serial schedule, then this kind of serial schedule doesn't exist. That means, so now this schedule cannot be view equivalent to any serial schedule. That is what this graph says. Understand? Now we'll see one more example and we check these things. Now we'll see this example and we check whether it is equivalent to some serial schedule or not using view definition. Take it. So first of all, points T1, T2, T3. Take the read condition. It is reading from database. Any writers? Yes, T2 is writing it. Then T2 cannot write before T1 reads. Then only that read condition will be satisfied. That's why T1 to T2. Next. So here reader, right? He is reading from database. No other writers before this reader, right? Especially B. Now we have other writers T1 comma T3 which are writing the same database item. Then they should not be placed before T2 to have the same condition. In serial schedule also, these two writers should be after T2. Definitely they cannot be before T2 for sure, right? That's why that means T2 to T1 there should be an edge, and T2 to one more thing is T3, right? T3 one edge. Though I know that since it forms cycle, there cannot be such serial schedule, but still let me continue. Last writers. Who is the last writer? There is only one writer, so no condition. So it is automatically satisfied. When there are multiple writers, we can get the order. Now see, write B, write B. So who is the last writer here? T2. Then in this T3 comma T2, always who should happen first in the serial schedule also? Easily we can understand that T2 should be last. That means T3 to T2. If you keep this order, then only T2 will be last in that writers, correct? So that's why T3 to T2. Again it forms cycle, right? Now whenever you form this kind of cycle, what does it mean? I will tell you. The serial schedule should have these conditions. What is that? And the T1 should be first after the T2. And another condition is T2 should be first then T1. That is not possible at a time in serial schedule. That's why this cycle indicates that, especially directed cycle, remember. So this graph is not view serializable because it cannot be view equivalent to any serial schedule because such serial schedule doesn't exist. Understand? Now we'll see one more example. Take this example. In this example, so again same thing we do, draw view precedence graph. So view precedence graph is only necessary, not sufficient. That means, so directly I will tell you what is the meaning of it. First of all, we construct view precedence graph. So read, you are reading from database. Any writers? Yes, T2 is writing, T3 is writing. They should occur after T1. So T1 to T2 edge, T1 to T3 edge. That indicates that. Next, any other database items? No. Then go for last writes. In last writes, there are two people who are writing T3 should be last. That means among T2 comma T3, T3 should be last. That means T2 to T3. T2 to T3. So these are the necessary conditions, right? So some of the conditions which I can impose are imposed here. There may be some other conditions I don't know, but these are the definitely necessary conditions. So if these conditions are satisfied by serial schedules, what are they? We will see. So I don't do this again and every time in the exam, but I'm just explaining you. So let's write all the serial schedules: T1, T2, T3, T1, T3, T2, T2, T1, T3, T2, T3, T1, and T3, T1, T2, T3, T2, T1. Now this says that really this schedule is equivalent to some serial schedule. That serial schedule should have this structure. Who will have this structure? We will see. T1 to T2. Yes, anything T2 to T1 in the schedules, this cannot be possibility. You understand. Similarly, T2 T1 order, this one T2 T1 order, cancel it. So two schedules got cancelled. They cannot be view equivalent to this one because of the definition, right? Now we'll see this edge T2 to T3. In serial schedule, the order between T2 T3 should be T2 to T3. Then cancel T3 T2 T2. Now cancel T3 T2. So this is T3 T2. Now we have, see, T2 T3 T2 T3. One more condition, T1 to T3. Take the schedule which is having T1 to T3, T1 to T3, T3 to T1, cancel it. So now you have only one serial schedule satisfying this condition. It doesn't mean that this is going to be view equivalent to this one, because only necessary conditions I formed, not sufficient, need not be sufficient. So that's why. So what to do, sir? Is it waste? No. Once you get, so what is the advantage of doing all this stuff is, see, I cancelled all other schedules which cannot be the answers. Now if and all if there is an answer, that means if and all if this schedule is equivalent to some serial schedule, this is the only possibility. Now you write T1, T2, T3. If you can imagine, that's okay. Like in your brain, if you can imagine the schedule, that's okay. Otherwise you write it T1, T2, T3. T1 means all the instructions of T1, because we are writing serial schedule. Read A, write A. Now T2, write A. T3, write A. Now check the view equivalence now clearly, all the conditions. Read condition, reading from database. Here also reading from database. Here any other reads? No. Now last writes. Last write is done by T3. Here last write is done by T3. Now perfectly this is view equivalent to this one. So remember it, one important point here. But for conflict serializability, once you get this graph, whatever. So once you get this kind of graph, previous one, whatever it is, let's say like this, if you get this kind of graph, T1 to T2, T2 to T3, then I can say that, example, this is conflicts graph, okay, conflict precedence graph. We know conflict precedence graph, right? So example, you have a schedule and you got this conflict precedence graph, then 100% this conflict precedence graph represents necessary conditions and sufficient conditions. That means the order whatever you are having in this conflict graph, so that will be a serial schedule T1 to C, T1 to T2, T2 to T3, that will form a serial schedule. Let's say if and all if it forms, that is going to be the answer. That means this serial schedule is going to be conflict equivalent to that schedule. But here that is not the case. Once you form the graph, then we have to identify schedules which satisfy that graph and take it, and again we have to finalize. That means again we have to check condition one more time. But for conflict serializability, that is not required. So to understand this point, what I do is I take a graph, I explain the same concept one more time with the example, so that you can easily connect to that one, right? Now we'll see the schedule and we check the details. Okay, first of all I check whether it is conflict serializable or not. For that I draw conflict precedence graph, conflict with respect to conflict precedence graph, PG. Let's do that. Take 3 points T1, T2, T3 and impose the conditions. First of all, there is a conflict right to right, correct? T2 to T1 to T3. Next, there is one more conflict T3 to T2. Yes, there is no other conflict. Let's stop it. And what I want to say is, this is necessary and sufficient condition. That means this graph whatever serial schedule satisfies this graph, definitely that is conflict equivalent to this schedule. Example, so this one is actually T1, T3, T2. Only this serial schedule satisfies this condition. So this is going to be definitely conflict equivalent to this one. Hence, so this is conflict serializable. In the GATE exam, they ask this kind of questions. They give a schedule. They ask whether it is equivalent to any, otherwise whether it is conflict serializable or not. Then answer is yes, because there is no cycle. Second one, what is the order? T1, T3, T2. The graph also gives you order. Now you don't require to check that serial schedule again to whether it is equivalent to this one or not, because this graph is going to be necessary and sufficient condition to find out the serial schedule. But for view it is not the case. Okay. So for view we will see now. Let's try view serializability. First of all, we have to put some necessary conditions. Let's call it as view precedence graph. So this view precedence graph idea is mine. That means, that may not be popular in the, other parts of the this terminology. That means other people may not be knowing this idea. What is that view precedence graph? There is a view polygraph, of course, that is quite difficult to draw, but that view polygraph is going to be again necessary and sufficient condition. But I am not teaching that. That is not required. For GATE, finally, what is our goal? Our goal is whether given schedule is equivalent to some serial schedule or not with respect to view definition. For that, first of all, I take again vertices like this T1, T2, T3. That means every vertex is one transaction. Now I will put some necessary conditions. Okay, I don't know the sufficient conditions. That's why what I do is I only put first necessary conditions. What are they? We will see. Go to read operation, you get one necessary condition. What is that? Since this read is reading from database, any competitors, any other writers you are seeing, yes, there is one writer T2, then he should not occur before T1. So that's why order between T1 T2 should be T1 first, then T2. This is necessary condition, right? So similarly, one more necessary condition, see, read of B. Read of B is reading from database, but any writers? No. That means what? There is no condition we can impose on the serial schedule with respect to this read. Now other reads, see here, this read. Any other writers? Yes, other writer. So T3 is reading, but T2 is writing, but it should not occur before that. So that's why order between T3 and T2 is T3 to T2. Anything else? So all the reads are done. Now go for writes. Who is the last writer? There are two database items which are having writes. So let's focus on one by one. This one, write of C. Here also write of C. Who is the last writer in these two? T3. That means T1, T3 are the writers. Among them, T3 should occur last. That means T1 should be first. The order will be T1 to T3. Understand? So next, anything else? We have one more write, that is write of B. But no others are writing. This is the only person who is writing. Then automatically he will be last writer. No condition can be imposed because of this one. Finally, because of some conditions, what I learned from my view definition, so I got this precedence graph, but it is not sufficient. That means, so whoever satisfies this graph, that that schedule may not be view equivalent to this one. Again we have to check. But sir, why you did all these things? Because of this graph, some of the serial schedules got eliminated. You don't require to check them, right? Because this is necessary. Now we'll see which serial schedule satisfy this condition. T1 to T2, we'll see. So this says that T1 to T2, T1 to T3, definitely T1 first. In such serial schedule, T1 should be first. Next, between T3, T2, T3 should be first. Anything else? That's it. T1, T3, T2. I got serial schedule T1, T3, T2. So that is going to be one of the potential candidate. But really it is a conflict serializability graph. That means conflict precedence graph. Directly it is answer. But now it is not answer. So I have to check it again. Let me check it out. So write T1, T3, T2, T1, T3, T2 in serial order. Right? T1, all T1 first. Read of A, write of C. Then all T2. So let me write here T2. So T2 here, T3 here. But we know that order is T1 followed by T3 followed by T2. If and all if some serial schedule possible. So T3, write T3, write C followed by read B. And then T2. So T2 has read B, write B. Now check that view equivalence definition one more time. So reading from database, reading from database, perfect. Read condition is satisfied. Next, this read condition, reading from database. So read B. So it is also reading from database because there is no other writers which updated it. Now another read, yes, here reading from again database. So T3 is reading from database. Here we have T3 that is also reading from database. Next, last writer. Who is the last writer of B? Last writer of B is T2. Of course, there is only one writer, so automatically T2 will be last writer. Now for C there are two last writer. I mean two writers. T3 is last writer here. So T3 is last writer. Perfect. So finally, now I am concluding that these two schedules are view equivalent. So since this schedule is view equivalent to some serial schedule, this is view serializable in that way. So we have to work it out on view serializability. But conflict serializability is a little bit easy because once you get the precedence graph, whatever the serial schedule satisfy that view precedence graph, that will be the serial schedule which is equivalent to our schedule. Understand? Now we'll take this schedule and we check whether it is conflict serializable or not. After that, view serializable or not, one by one. So first of all, we go for conflict serializability, and we know that we form precedence graph T1, T2, T3. Let's begin here. So write read conflict, that's by T1 to T2, and here there is a conflict T2 to T3, that is read to write, correct? So T2 to T3. Next, see here T3 to T2, write read is a conflict on database item, same, right? So finally it forms cycle. Whenever it forms cycle in precedence graph, that schedule cannot be conflict serializable schedule because there is no schedule which is equivalent to this schedule which is serial. That means there is no serial schedule which is equivalent to this one. Then you form a cycle. Now we'll see view serializability. For that we form view precedence graph. Let me do that. T1, T2, T3. Remember one thing, this view precedence graph is not sufficient. It is just necessary. In this graph, if you form cycles, definitely that schedule is not view serializable. If it does not form cycle, then what we have to do is necessary condition is satisfied but may not be sufficient. That means still we have to check whether there is a serial schedule or not. But why are we doing? Already I told you so many times. If you form this kind of conditions in view serializability, at least we can reduce the number of possible candidates, right? So we'll see that now. Slowly you'll understand after this example. First of all, read condition. So this read is going to give one necessary condition. What is that? Since this read is reading from T1, so definitely the condition between T1 and T2 is T1 to T2 for sure, correct? Now, see why it is necessary, not sufficient, I will tell you. There is one more transaction T3 which is writing, correct? So this write of A, if it is kept in between, then this will not work, right? So then your T2 cannot read from T1. So one more condition is there, we are neglecting it. What is that? There is other writer who is writing it, correct? A, then that writer should not be in between, but that writer can be before T1, maybe after T2. So this kind of condition is very difficult to represent in the graph. That's why, so this graph represents only few conditions, but there are some other conditions like this one. What is that? This write, if it is kept here, then you will violate the read condition, correct? Because T2 should read from T1. How can you keep write here in between these two? So not possible. But it does. So where to keep write? You can keep here, otherwise here somewhere before T1. Then still read will read from T1 only. But that condition, whatever now I explained you, it is very difficult to represent in the graph. That's why usually, so all the conditions are not represented. Only few conditions are represented. We will see that first of all such few conditions. The one of the few condition is take every read and see the other writers. So ask first question, Mr. Reader, from whom you are writing, you are reading from T1. That's why T1 to T2. That is one condition. Take one more condition. See, read of B. Mr. T2, you are reading a database item B, right? From where? Immediately from T3, correct? So T3 to T2, correct? Let's write. Next. Any other readers? So reader, reader, done. Now go to last writes. What are the last writes we have? One is last write on A, last write on B. So how many writers are there for A? 1, 2, 3. Out of them, who is the last writer? T2. That means T1 and T3 also writers, but T2 should be last. I can say like this, T1 to T2, T3 to T2. Let's put that conditions here. T1 to T2 is already there, T3 to T2, T3 to T2 also there. Now go for another write. What is the last write for B? See, this one, correct? But how many writers we have? Only two. What are they? One is T3, another one T2. What is the relation between them? Definitely T3 followed by T2. That means T2 should be after T3. So T3 to T2. Yes, we already imposed it. So finally what I want to conclude is, go for another write. What is that? Write B, correct? So here T1 is writing and T3 is writing. So T3 comma T1, out of them who is last? T1. That means order should be T3 to T1. So this one, T3 to T1. So finally some of the necessary conditions are imposed. So because of that, this is only necessary but not sufficient. So now using that, so do you get any cycle here? No. That means, so there is a possibility of having some serial schedule which is equivalent to this one. But if really it is conflict serializability graph, that means conflict precedence graph, directly I can say that out of them T3 first, after T3 either T1 or T2, but the order between T1 T2 is T1 to T2. That's why this will be the serial schedule which is equivalent to this one. I can say that when, if it is conflict definition, but in view definition it is not possible. Already I explained you, because these are only few conditions you imposed, not all. That's why what we have to do is to check all the conditions. We know what are all the conditions. What are they? Read condition and write condition. That is the original definition, right? So we'll go to the original definitions by taking one potential candidate. Who is that? T3. So these conditions are satisfied by only one serial schedule, that is T3 followed by T1 followed by T2. So what I want to say is, this method, whatever the view precedence graph method you are using that, I filtered all that other 5 schedules and they cannot be the potential candidates. Now it doesn't mean that he is potential, but at least we have a possibility for him. Let's finish it up. So now let's check the conditions one more time. T3, T1, T2. I write T3, T1, T2 order here. T3, T1, T2. First all T3, write A, write B. Next all T1's instructions, write A, write B. Then all T2 instructions, read A and read B and write A. For this serial schedule, we have to check the equivalence. Let's begin. Take every read operation first. So this is read operation. It is reading from T1. Now we have original schedule. In that you really check it now. Mr. Read, from where you are reading? See, definitely from T1. Perfect. Read condition is satisfied. Take another read. What is another read? Read B. So Mr. T2, you are reading B from where? So definitely T2 is reading B from, if you see in this one here, T3. But here there is one more write. Correct? Here there is a write here. But since because of other conditions, T1 is pushed. Otherwise T1 is pushed into this I can say order first, and because of that now this read is reading from T1. But actually what should happen? See, T2 should read from T3. T2 is reading from T1. But we did not cover that in the precedence graph. We were not able to cover it. That's a problem with view precedence graph, because view precedence graph can cover only few conditions. Understand? So whatever the, and one more thing, this view precedence graph is only, just I formed it. I don't know whether it really such kind of procedure exists or not, but using that we are going to reduce the problem size and we are saving a lot of time. Understand? Now finally this is about view precedence graph and its uses. Now in the GATE exam, if they give any question, first of all form view precedence graph, then form one serial schedule or two, depends on the structure of the view precedence graph, then do this activity. So now here when I did this activity, I realized that these two are not equivalent. So now there is no such schedule. Finally we had only one potential candidate and I applied for that, the condition, the definition of view serializability, but it did not work out. Correct? Just now you have seen. So finally there is no equivalent schedule for this schedule which is view equivalent. That means this is not at all view serializable schedule. That's it. In that way you can answer any question related to now conflict serializability and view serializability in GATE exam. In GATE exam they ask 90% of the time questions from recoverability and serializability. I can say 80%, not 90%. And especially that questions are, they give schedule and they ask, is it conflict serializable? Is it view serializable? That kind of questions. That's it. And we can answer it. Now we'll see computational expensiveness of checking conflict serializability and view serializability. So assume that let's say we have precedence graph. Whenever you have conflict precedence graph, CPG, so it will look like this, right? T1, T2, T3, T4. Let's say this is your typical graph like this, T1 to T2, T3 to T2, T4 to T2, something. So T3 to T4, whatever. So in this graph, finally, given a graph, we have to know whether that graph has a cycle. If this graph has a cycle, then your schedule is not conflict serializable. Otherwise, it is conflict serializable. That is the definition of conflict serializability, correct? So that's why simply check for the cycle. Already I told you how to check the cycle in data structures and algorithms. Please attend my data structures algorithms classes and you know how to check the cycle in directed graph, and we proved that it takes only order of v plus e time, correct? You just apply DFS algorithm. So order of v plus e, where v number of vertices, e number of edges. So here transactions are the vertices. If your graph has n transactions, that means if your schedule has n transactions, it takes n plus number of edges in this one, right? So n, I can say that number of edges definitely will be not more than n square, correct? So number of edges are always less than or equal to number of vertices whole square. We know that, right? According to graph theory. So asymptotically. So n plus n square is nothing but asymptotically n square. Rough idea. I can say that we can have order of n square algorithm to check whether a schedule is conflict serializable or not. But checking view serializability is difficult. The reason, so though you have view precedence graph, what can happen is your view precedence graph, let's say, doesn't have any edges T1, T2, T3. If there is no cycle, it doesn't mean that, so there is, it doesn't mean that it is view serializable. What to do if there is no cycle in this graph and no edges? Then what to do in the worst case? Then we have to try all possible serial schedules which can form with this condition. In the worst case, if your fate is bad, there will not be any cycle, then all the serial schedules satisfy the condition. That means this precedence graph produces all possible serial schedules which are n factorial. Now for that n factorial, we have to check again that view condition. Each takes at least 1 unit of time, just assumption. Still to evaluate n factorial possibilities, it takes lot of time, and that's why view serializability condition checking is NP hard problem. And one more thing, you don't know what is NP hard, right? Please ignore, just remember this word. Second one, it is exponential. That is enough. That means n factorial serial schedules, in the worst case we have to evaluate. There is no skipping, there is no other option for you. That's why it is exponential in the worst case. And NP hard, that means no one can reduce its time complexity usually, but don't worry, you don't know what is NP hard, right? So when I teach you TOC, at that time I teach you what is NP hard and NP complete. By that time you will be learning what is NP hard and NP complete. Okay, now we'll see one more important point, which is about aborted transactions. Whenever you have a transaction with abort, otherwise you have some aborts and commits, then how to understand this kind of schedules? Very simple. Though this aborted transaction, we know what is aborted transaction, right? We are going to cancel it. So, and all its effects also. Then when you are having this kind of schedule, then T1 is going to interfere with T2 and T3. But however, we are going to cancel that interference, right? Because you are cancelling the transaction and all its effects. So finally, what I want to say is, so there is no role of T1 in this concurrency, right? So when you have aborted transaction, we should cancel it and we should not consider in the calculations. Then you will see only one dependency, that is T2 to T3. So finally, this is conflict serializable. If you consider this also, then you get wrong answer, because when you do take this one also, then it is not conflict serializable because there is a cycle. See, read to write, write to write. So T1 to T2, T2 to T1. Similarly, I think this is not view serializable also. Whatever, doesn't matter. Finally, my answer is, whenever they give a schedule with some aborted transactions or some rolled back transactions like this, rollback, then simply cancel that in the schedule, and for only committed transactions you have to calculate the serializability. That is what the final thing.